Let's start. Today I will talk about what our work is currently doing, what we are currently doing in Amadeus. I have presented quickly this morning what Amadeus is, but basically Amadeus is a company that works in travel industry. Our client is mainly airlines. So our business is actually, we receive contents from airlines, and then we distribute to all travel agencies in the world, and this travel agent will then sell the content to the travelers. This is our first and main business 20 years ago, but now we also provide the IT solution directly to the airlines, right? So this is about Amadeus. We have been around since 20 years. We have offices all around the world, including in Berlin. But our R&D mainly is in Nice, in France. But we are all over the world for R&D as well. We have a center in Bangalore, in Boston, and in Bangalore, Boston, and in Madrid, Spain. I myself based in Nice, France. So the outline of our talk today is organized this way. We will see why we do this, and then we go deep into detail about the decision trees and how we implement and the conclusion. I've discussed already with many people asking me whether it is a talk about Flink machine learning library. It is not. It is really about our implementation using Flink streaming API and many other libraries. But we of course have a look at what is going on in Flink machine learning. We really want to use it, but at the moment we find it is slightly not what we want at the moment. So what we want to achieve is actually we need a classifier that is able to work with data that comes in streaming, but also, so we need to classify data that come in streaming, right? But also we want to learn from those data that come in streaming. So these are the two things that we want to do. The use case is, so if you search for fares today, you will typically be shown this kind of calendar of prices where you have $90, $75, you have the lowest price, you have some days are sold out and so on. But now airlines, our clients, our customers, wants to give more sense of urgency to buy the ticket. So we want to add some more information on fares that are there. You might have already seen, but if you really into the industry, you will understand that the fares are really volatile. It's quite difficult to even for airline to know whether this will increase tomorrow or not. If you ask somebody in Ireland, how would be the price of today for a given origin and destination, it might not be that easy. So we provide this information, and to be honest with you, we have already a system that does this during completely in batch mode. So we use our historical data and then use it for doing this classifications. But now we are looking at the streaming part for two things. The first one is that because the data is actually coming in streaming, right? So we think that it is more natural to work with the streaming algorithm. But the most important thing is that we want to be able to cope with the change, or what in machine learning or data mining, what is called drift, something like that, that we will be able to change our model more or less in real time, but at least faster than our batch prediction system. Another point of view is, again, from airline point of view. This is for sales of airline. We want to, this is the view that typically an airline will consult every day to see their status of the sales. We again want to know what to give an alert, not an alert, just classify for a given date or a given month. This is a month, but actually it can go until the daily. And again, we want to classify the information in real time. So again, here's what we want to achieve. We need a classifier that works in learning. The data that needs to be classified is in streaming, but also the data that will be used for learning is in streaming. So what are these basically mean? It means that we want to keep our model as fresh as possible. Today, what we have in production, we have a system that learns every week or every month, depends on case, but always using, say, 1 year of data, right? Historical data. It's quite difficult to change the model because, yeah, it takes some difficulties in operational modes. So the second one that we want to see is that today we have systems that can be introspected. So we know that here's the tree that we use, and here is why we provide classification. So we want to reach the same thing for streaming. So this is the this what we mean by introspectively. We want to introspect the model in real time as well. And the third one is that we want to be able to have a seamless support for the whole workflow of machine learning, especially for pre-processing. Why it is important for us? Because if you see the case I presented, the thing is that the label data that we have is somehow skewed to some popular origin destinations. So it will be good for predicting popular origin destination, but maybe for less popular it will be more difficult. So we need to do some rebalancing of the data, pre-processing, data imputation, things like that. That we want that if we have something in streaming, we want to have this as well. What is nice to have, this is a must. Yeah? What is nice to have is that the classifier is immediately available. So it's not our goal really to be able to have a classifier that adapts directly the data that comes and learn from this right away. But what we want is that the classifier, well, this is not really our goal. Our goal is that it will be available a little bit faster than what we have today, but it should not be taken into account right away when you come and then I change the system. No, it is not the goal of the system that we are trying to build. What we are trying to build is we try to be as close as possible to the decision trees in batch mode, but we want to make it faster and more adaptive. And the second one, it is more longer term goal is that we want to have several implementation of classifier for real time, and we want to be able to pick the best algorithms that work for a given time for a given set of data. So this is what we call meta-learning capability. It is not there yet, but our goal is at the end we'll try to achieve the full system that have this capability as well. So yeah, this is nice to have. So here's if there's one slide that explains what we are really doing is actually this slide. So we start from learning. The color represent the class of the points. We start learning, and at a given time, it is still learning, but it says that at this time, I can already start classifying things at this time. So it can start to receive unlabeled data and then start classifying during its learning. And it will achieve an end of learning sometimes, and then it will go to the production. Well, it goes full tree that is just like the usual decision trees. And then it can restart the new cycle of learning without intervention. Okay, so here is basically the architecture. So we receive the data coming from Kafka. We have the stream learner that we implement in Flink. That it will create a stream of decision trees, right? So some of the trees that are generated are actually still under learning process. It's not the full yet ready, but it's already there, able to classify. And of course, at the end of the application, there will be a classifying application that consumes the decision trees that generated by the learner. Okay, so how many of you are actually quite familiar with decision trees? Okay, so there are a couple. So I will have a quick view of decision trees. So at the very beginning in 1984, there's this paper from Bryman that tells what decision trees is about. And then in 1999, there's another paper written by Bryman in 1999 that talk about random forests. And then in 2011, there's this interesting paper that explains the use of decision trees or random forests in Kinect. What about the streaming decision trees? Maybe you have already seen this Hofding tree or VFDT, a paper by Pedro Dominguez in 2000. It is not what we are doing. What we are doing is more this one. So this paper is our base of work. So the difference with the first one is that we really build decision trees. We have the end of learning phase. We have this production ready tree and a tree under learning. So this is why we take the second approach. So if you are familiar with decision tree, well, I just take a quick look at what decision trees means from my domain, which is the reservation subspace. We want to classify whether a trip is a business or leisure trip. So what we want to do, yeah, maybe there's some red. Advanced purchases means that how long the purchase is to the trip date, right? So somebody that there is very nice. The red one is there, even though it goes for business trip. It reserved long way before and with the lowest class possible. And there is another one, Brad Pitt, that always purchase the day before the trip and always at the business class. So we want to classify the trip into two, the business and leisure. So first, we split the points into two, into the yellow point, for example. And then we split further, and then we reach here. So we have the blue one is the leisure, the red one is the red, and the composition at the leaf tells give you the idea of how good the classification is. So the classification works like this. So if you have a point there, we first, that resides over there, we compare against the line of the yellow line, and then we see that it is up, so we go to the right, to the violet one, and then we say that this one is business. Okay, this is decision trees, which basically you can see decision trees as well as a problem of optimizing the partition. When we try to optimize an information gain here, for example, if we split the two data set here, it will not be optimized in terms of information gain, which is explained in this formula. But if we put here, then this is a good split because it maximizes the information gain of this formula. Okay, so now what about the streaming one? Well, the difference is that the batch version of decision trees require few of the full learning data set. While in streaming, the thing is that we can each point only once. And second, the processing should be fast. We can't afford to have too much access to the disks. So the intuition of the algorithm is that instead of using every point, we compress the points. Okay, and instead of knowing where each point is, we approximate their positions instead. Okay, so the intuition, we'll see again this problem. Here's the points, but we can't see everything. But instead, we compress them, and then we work only with subset of it, very, very small subset of it. And then we have the information, we store the information of how many points nearby the points. Okay, so this is the intuitions. And the rest of the work is still the same. Okay, so the question, okay, we do like that. How to find, so the basic question is that how to find split points of the streaming decision trees. So I said before that we compress the data, meaning that for each features label, we create histograms like this, okay? And then, so we have a lot of label and features, and then from time to time, we merge them, and we ask whether it is time to split or not, right? So before splitting, we want to get the split candidates. In the batch version, you will see each point and then see if we can split here with these features or not. What we need to do in the streaming one, we need to first uniformize, make the number of points for each interval that we want to see to have more or less the same points. It is approximative, of course, but we try to get the number of points for each point that we want to check to be at the same, to have the same number of points. Okay, so and then from there we determine the split. We're using the same formula as before, using the information gain, using how much how much for a given point the information gain that you will have by splitting at that point at that feature and that label. Okay. So okay, I lied. the intuition is not exactly precise, because actually, if we do this, okay, and we do this, there's a problem that the histograms can no longer be used for further split. And of course, we have already lost original data. So what we do? This is something that is not clear if you read the paper that I cited before. And we think that what we propose here is maybe the solution. It is a solution for us. It works fine at the end, but maybe we have different approach. So here's the solution. So for each iteration, we actually use different data sets. So this is the first iteration of the data. We build the first node, and then we build the split. For the second layer, we use the subsequent data set. Actually, that comes, remember the data comes in streaming, so we use the subsequent data for doing the splitting at the subsequent level. And so on, right? So that's the idea. Okay, maybe if you have not enough data, maybe you just can re-inject the same data, and Kafka is very good for this because you can rewind and reuse the same data for each level. But this is not what we're doing. What we do is that we do the split with different set of data for each iteration. So we're almost at the end. So the implementation. So here's the architecture. So we start receiving data for, we start receiving points for learning from Kafka. We inject it to Flink, and then whenever we think that it is good time to export the tree, we will put the tree to the Kafka, to another Kafka. But also, we actually put to Kafka a tree that is not completely finished. Right? For two things. The first one is that maybe the tree is good enough for classification job, but also in our algorithm we need it for doing subsequent iteration. So that's how we do it today. Maybe the expert of Stream API will tell me, this doesn't make sense. So I will be very happy to take some inputs. Okay, so yeah, the reason why we do this because we need to annotate each message with the tree so far. So this is the code outlines. So the first two lines are how we get are the codes on how we get the data for two different streams, and then we annotate them using connect and then flat map. And then we create the histograms. We create the small histograms first, as you remember in the algorithms. And then from time to time, we merge them into a bigger histogram. And then at that time, and we determine if we have enough point and we are good enough to split. And if it is the case, we select the point that maximize the information gain of our trees. And you see the last point there, and then we split at that time, and then we generate at that time another node, and then we put it to Kafka here. Okay, so this is the outline of the code. Of course, I remove a lot of things, bells and whistle things. But actually, it's not that many I remove from here. It is the implementation is very very nice because the API is very nice for us. It works very fine. And by the way, if you see this, this is our attempt to work with 0.10 version. For 0.9, it has a slightly different, but it is our attempt to work with 0.10. So maybe still strange things happen. If you see the code, again, I will be happy to take any input. Yeah, so what I was saying is that the API worked very nice for us, and at the end, the Flink code, the Flink-related codes are quite minimal. The codes that implement the logic of decision trees are much, much bigger than the code that have Flinks inside, which is very, very nice for us. Okay, with this in mind, we actually experiment something even different. So we said that for each iteration, we implement a node, but actually we do much more than that. We build several trees, a small one, but also we build bigger tree that consume bigger data. So you see that here, what I try to describe here is actually the whole data that is used to build the first small tree. Actually, we use it for to use a bigger tree. Why we do this? Because we want to actually build several trees with different number of data that are taken into account, and then at the end we kind of implementing the vote of the result of each of the tree. So this is why this is what we are doing at the moment. So the conclusion. In this talk, I have explained the approximate histograms for building decision trees. I also describe our approach to build this instead of, for example, taking Hoeffding trees, because we really want to be as close as possible to the conventional decision trees. But with this, we have achieved what we want to do, which is we want to have a freshness of the classifier and the system that continuously learning. And again, I have also mentioned before that Flink together with Kafka allows us to do this in a nice way. We started actually using Spark streaming, but with Spark streaming, the problem is, if you know Spark streaming, the fixed window is really hurting us. So that's why we think that Flink is the best choice for us here. So the next step we're going to do is the random forest. Somehow we have already started the work by taking into account different, by building different trees with different set of data. But we want to also implement the random forest that's randomly selected features at each level. We also want to implement the meta-learning possibilities later. But our focus at the moment is really on the pre-processing data that we find it very, we don't find a good implementation either in Spark or in Flink. And we don't find a good pre-processing streaming for machine learning at the moment. So that's that's where we will focus on the next couple of months. Okay, that's actually the end of my presentation. Thank you very much. So I think we have time for questions. A lot. So questions or input? We are kind of beginner in Flink, right, Stefan?
I think you're actually not so much beginners, right? I think you're also, for the streaming API, one of the comparatively early users, I would say. That's maybe a good question, given that you started with, let's say, 0.9 streaming API, and you said you just forward fitted it to the latest version. Did this work like smoothly, or were there like concepts that were like hard to adopt when the APIs changed?
We had a hard time, yes. We had a hard time to try to move from 0.9 to 0.10. We spent some days or even weeks to figure out how things are organized in the new Flink Stream API. This time window that changed. What else? Yeah, there are many packages that are reorganized. So yeah, it was quite hard experiment, but we know, of course. We just want to experiment it, moving from 0.9 to 0.10.
Okay, so was it mostly, classes that are now called different, or packages that changed? Also, I mean, some of the concepts that were a little tricky, we eliminated them again, and on the other hand, we introduced some new. Did you actually stumble across that, or was that did that work out?
I didn't get the question, sorry.
Okay, I mean, other than just changing, let's say, packages and classes and so on, what we also did is there were some things like co-window operators that had a bit of a not very well-defined behavior, that we said, okay, let's actually not include them in our 10, and let's see if we can actually learn how to make them more predictable, maybe reintroduce them later. Did any of this hurt you, or was that
yeah, as you can see, we don't really use fancy things from streaming API. We just use connect, flat map, time window, kind of stuff. We spend some time to work on iterate, the iteration of streaming, because you see that we actually need to fit back to the system the current tree, but actually we couldn't figure out how should it work. So, but anyway, we need to produce trees from time to time, so that's why, okay, forget about iterate of the provided in streaming, which might be interesting, but we just do our own feedback mechanism by putting it back to Kafka and then consuming it later. But maybe we can talk offline why we didn't manage to work with iterate, but yeah.
All right, thanks.
Any other questions? Okay, so if there's no other questions, well, I will be around. And if you know somebody who is happy to work on this kind of project for their internship, we always open for this kind for internship. Or if you want to join us, we might hire as well. Just approach me for that. Thank you. Okay.
I actually have a final question. And so, given that there's not yet a machine learning library for streaming in Flink, there's basically, as a library for machine learning in Flink, there's only a connector to Samoa. Have you actually, okay, it's actually two questions. First of all, have you looked into Samoa? I think there is an implementation of decision trees as well there. Is that something that is very specific to your use case? That's why you implemented basically your own algorithm versus versus using the one from the library. And second, would you be? Is this very much Amadeus internal, or would you be willing to contribute this to the open source project?
Well, this is not our main business. So our business is in travel. So everything is not in our business. Will typically go to open source if it is good enough. So yeah, it will go to open source when we think it is good enough. The second, the question about Samoa. We, of course, want to learn about Samoa. We just don't have time to explore Samoa. We are starting seriously having a look at it this week, this month. So we'll see what it will give to us.
All right, thanks.
Thank you very much.